Hello everyone, welcome to Adam. So now we are going to solve this question which is based on SFT and BMD, where we have been asked to calculate where we have been asked to draw the SFT and BMD of the following B. As you can see in the boundary conditions, we have yield support at A, the roller support at G, and some point forces at B and C, and certain movement at F, and the UDL between DE. So let us see how we can solve this. Firstly, we need to draw the FBD of the following field, which will be helpful to find the support reactions. So to find the supports. Second, we will find the shear forces, and third, we'll find the bending moments at every point to calculate the SFT and BMD. So first step becomes this drawing the FBD. So let us see how we can draw this FBD. Firstly, we have at point A, so let us say this A, B, C, D, E, F, and G. So at G, we have a roller support, so we will give a vertical reaction force, which is at G1, let us say. At A, we have a yield support, so we will give reactions on in both the direction, which will be one at X in the X horizontal direction and one the vertical. So vertical one, let us call it FAY, and horizontal one, let us call it FAX. At B, we have a inclined force which we need to resolve. So one resolution will be 60 into like cos 45 and 60 into sin 45. So this will be 60 into sin 45 one, and this will be 60 into cos 45 one in the horizontal direction. And at C, we have a 100 Newton force acting downwards. Between D and E, we have EDL, which we will convert into a point load, and which will be 50 to 200, acting at 1 meter from D and 1 meter from E, because the centroid is at the midpoint of the D. And at F, we have a certain movement of 400 Newton meter. At G, we have roller support. So yeah, that is how you can draw your FBD. Let us just mention the distances also. We have A to B as 1, B to C as okay 1, C to D is 2. D2 is 2, but you can just say it is at 1 1 because of the UDL conversion into point load. It will be at the midpoint of the UDL, the UDL. So we can say that the force is acting 1 meter from D and 1 meter from E, which is the midpoint of the ball. We have EF distance as 3, and FG distance also as 3. So the total beam length will become 12. So here 3 plus 3, 6, 7, 8, 9, 10, 11, 12. So yeah, 12. So yeah, this is how you can draw your FPD and mention distances. So let us see how we can solve this. You need to apply the equilibrium condition here, which will be summation of x is 0, summation of I is 0, and summation of moment at any point is 0. So summation of fx is 0, when you apply, you will get as fx is nothing but 60 cos 45 in the negative direction, which means that the reaction at A should be in the opposite direction, which will be in this direction, FAX. Yeah, so that is how you can draw from this that fx is nothing but minus 60 cos 45. And nextly, we can apply the summation of y is equal to 0 condition. So all of these are equilibrium conditions. So equilibrium condition these are, and we have summation of y is 0, which will be FAY at A minus 60 sin 45. So we are considering upward force as positive and downward force as negative. You can change this; it won't affect your final solution or the equation, which you will get through this. We have 60 sin 45 in the downward direction. We also have 100 Newton force at point C in the downward direction. We have 100 Newton force at the UDL because of the utility D. We have an FGY force in the acting in the upward direction, so that is why it is taken as positive. The final equation becomes FAY plus FGY is nothing but 200 plus 60 sin 45. It will be 242 was 42 as our equation number 1. And the second equation will be from the movement, which will be this third condition which you will apply. So you can apply this condition at any point in the beam, but more often than usual that we apply it at A or G. Why we do that? Because the FAY and the FGY force will disappear because of that. So if a force is going through a certain point, let us say a force F is going to point A, and you take a movement at that point A, then that force, the movement because of that force will not be there because the distance will become zero. And movement is nothing but force into distance. So that is why if you take the moment about point A, then the FAY force will not be there. So that is why we'll take it at particularly at A, because then we will only have GY in our equation as the unknown force, and we can directly calculate that unknown force. We have moment at A, so summation of moment at A is 0. And we have 60 sine 45 into 1. So 60 sine 45 into 1, because it is force into distance and distance is 1. So all the distances we will be calculating from point A. We have 60 sine 45 into distance is 1. And it is a clockwise movement, so we will take it as positive. So clockwise is positive, anti-clockwise is negative. Again, you can change this, it won't affect your final equation. We have plus 182 because clockwise movement, and 100 is the force and 2 is the distance because of point force at C. We have plus 100 into 1 plus 1 2 plus 2 4 plus 1 5. Because of the UDL, we have this 100 into 5 as the movement, minus 400 because of the movement at S, and it is in the anti-clockwise direction, so that is why it should be negative, minus SGY into the total distance is 12. So 1 plus 1, 2 plus 2, 4, 6, and 6, 12, yeah. And this is because of the reaction force at G. So yeah, that is how we can calculate the equation. You can solve this equation by using your calculator, which will be 60 to sine 45 plus 200 plus 500 minus 400 divided by 12 is 28.53. So FGY becomes 28.53. So if you put this equation into your, if you put this value into your first equation, you will get the value of FAY also, which is 0.42 minus your answer, which will be 213.88. So 230.88. Let us just add this. We have 28.53. Oh, okay. Just make it either you can make this at 28.54, because the total addition should be 242.42, nothing else. So you can just make it as 28.54, or either you can make 230.89. Whatever you can assume or approximate from the values you can get into your calculator. So we have a FGY as 28.54. We have FAY as 213.88. So these are our reaction forces at A and G. So after we have found the reaction forces, we can just find the shear forces at every point and bending moment at every point, and then make the BMD and SFD. So yeah, for that you need to follow certain sign convention for the calculation of shear forces. Until now the sign convention, even if you change it, the equation will be same, but now you need to follow that like strictly, because it will affect your solution now. So we have, for the shear forces, if you are calculating from the forces on the left, then you need to consider upward forces as positive and downward forces as negative. And or you are considering forces on the right, then upward forces should be negative and downward forces should be positive. What I mean is, let us say you have something A, B, C beam, and you are calculating force at C or at B, the shear force at B. Then either you can consider forces on the left, which is the A side, or on the right, which is C side. So if you are considering forces on the A side, then you can use the first sign convention, which is the left side one sign convention, or on the right side, then we can use the second sign convention. So that is how the sign convention works for the shear force one. We have shear force at A is nothing but the reaction at A, which is 230.88. Shear force left of B, so just left of B. So whenever you have a sudden force, which is what we have at B, C, and the last point, which is the reaction force at G. So we need to consider left side of the cross section and right side of the cross section at that particular point, because it will suddenly change at that point. So you need to understand how it is changing. So we will consider left of that point and right of that point whenever you have a sudden force at the particular point. Shear force left of B we will have as a 230.88 only, because there is no force between right of A and left of B. So shear force just right. So right of the B when you are crossing the beam, then you need to consider force or this force also 60 sin 45. So 213.88 minus 60 sin 45. So you can calculate into your calculator 230.88 minus 60 sin 45 will give 171.45. And you have a shear force left of C, which is the same, which is 171.45, because again there is no force between PC, right of P, left of C, there is no force. So shear force right of C. All of this we are calculating considering force on the left only. So that is why if you observe the sign convention, we are considering force on the left only. So this is the left of the C. So we are considering all the force on the left. And if we are considering on the right of the C, then also we are considering all the force on the left. So the cross section doesn't matter. We for now are considering all the force on the left of the cross section whenever you cross the beam, crossing the beam. So if you cross the beam shear force just right of the C, then you need to consider all the force on the left, which will include this 100 Newton force at C. So 171.45 minus 100, it will become 71.45. Then we have shear force at D, which will be 71.45 only. We have shear force at E, which will be 71.45. Sorry. Minus 100, which will be 71.45 minus 100 is a minus 28.55. And if you go it at G, so shear force at F should be same, which is minus 28.55. And now shear force at G will approximately equal to 0, because minus 28.55 from the left, and there is a reaction of 28.54 at that particular point. So it will come out to be 0 approximately. And the shear force at that particular point should be always 0. Like whenever there is a on the right side, so there are two extremes on the beam, so A and G. So on the right side extreme, it should come out to 0. The shear force should come out to 0. So that is how you can also check your solution if you are calculating the shear force is right or not, because the shear force should go to 0 at point G. So yeah, we have a shear force at A as 230.88. We have so let us just draw it a little bit downwards. We have 213.88, so it will be A, B, C, D, E, F, and G. At A, we have 213.88 as the shear force. Left of the B, 213.88 only. And the right of the B, 171.45. So 171.45. And left of the C, we have 171.45 only. And right of the C, we have 71.45. So 71.45. At D, we have 71.45. At E, we have minus 28.55. Minus 28.55. And at F is same. At G is same. And just at G, it is going to 0. So it will vary something like this. And whenever there is U there, it will vary like a linear, like an inclined line. So yeah, that is how you can. This is how you can draw your shear force diagram, but just by joining the all the points which we calculated using the shear forces, then use that every point. So you can use that calculation and then put the values in your like table, and then you can calculate. Uh, just join the points which you calculated. You can draw the shear force diagram using that. Just you need to understand that whenever there is a UDL, you need to vary the force linearly. So yeah. And if you like observe this here, we have a 71.45 and minus 28.55. So at D we have a 71.45, and it is decreasing because of the UDL, a downwards UDL, and it is going up to minus 28.55. So somewhere in between it should go to zero, right? So that is the point we need to calculate also, because we have been saying that whenever the shear force is zero, the bending moment is maximum, because of the shear force is nothing but dm by dx. So whenever the bending moment is maximum, the shear force should be zero, or minimum also the shear force should be zero. So we need to consider this point where the shear force is going to zero, because we will calculate bending moment at that particular point, because we know that it is going to be maximum at that point. So 17.45 is the force just before the UDL, minus there is a 50 Newton per meter acting, and let us say at some point x it is going to zero. We have that point zero. We have the shear force at that point zero. So 71.45 minus minus 50x is the zero. So 70.45 divided by 58 will become it comes out to be 1.43. So 1.43 meter from D, the shear force is going to zero. So that is what we have calculated, that x is equal to 1.43 from D, it is going to zero. So we will just see what is the point of calculating this. Then we can make the bending moment diagram. Yeah, we have a bending moment at A and G as zero because of the equilibrium condition. We have a bending moment at B as also the bending moment sign convention is something like this, that whenever you are calculating from the forces on the left, then clockwise should be positive and anti-clockwise should be negative, and on the right, clockwise should be negative and anti-clockwise should be positive. Then you can say that bending moment at B is nothing but the reaction force at A into the resistance, which is FAY into 1. So let us say you have crossed the wave somewhere here at B. So you have on the left side. So on the left side, the clockwise will become positive. So and it is a clockwise movement only. Yeah, so it is a clockwise movement. So we have FAY into 1, which is 213.88 into 1 as the clockwise movement, which is 213.82. We have bending moment at C. So if you calculate this at C, so this is, let us say, somewhere cross section, we just write this. Yeah, if you cross the wave somewhere here at C, you can see on the left side that there are how many forces are there. So we have FAY, which is nothing but 213.88. 213.88 into the distance between E to C is 2 in the clockwise, minus 60 sin 45 into 1, because it is an anti-clockwise movement, and it will become something like 213.88 into 2 minus 60 into sin 45. We have 385.33. So bending moment at D, if you let us say cross the beam somewhere here and calculate from the force on the left now, only left. So you can also consider force on the right also. because but we will consider on the left. The answer will not change. The answer should come out to the same if you follow the sign convention carefully for the right and for the left. So for the left, we will calculating. So we have 230.88 again. Into the distance is 4 now, and it is a clockwise movement, minus the 60 sine 45 1 into the distance is 3 now, minus again because of the sudden force at C, it will be 100 into 2. So we have a 213.88 into 4 minus 60 into sine 45 into 3 minus 200 as a 528.24. We have a bending moment at E. Let us calculate the first at point X, which is we are saying that it is a maximum at that point. So let us calculate bending moment at X, for which the free body diagram can be also drawn. So let us just remove this sign convention with. Yeah, we have. Let us draw the right side FBD. We have. Okay, yeah, we have F of the GY. We have this point here. Let us call it a D point. We have this point E, F, and G, and there is a sudden movement at F of 400 in the anti-clockwise direction, and we have a force of, yeah, we are calculating at 1.43 meter from D. So there is something 1.43 from D. This is where we are calculating the bending moment and calculating from the right forces. So the remaining UDL, which will be from X to E, will always be there. So the remaining UDL is nothing but 2 minus 1.43, which is 0.57. So because of this 0.57 distance, there will be a certain UDL, the value of which will be 0.57 into the UDL value, which is 50. So 28.5 force will be there. So this is 28.5 force. And the distance, of course, will be 0.57 divided by 2. So 0.57 divided by 2, we have 0.285. So the distance is 0.285. And the moment at that point will be nothing but FGY into the distance, which will be E to G is 6. E to G is 6 plus 0.57. So 6 plus 0.57. 0.285. Yeah, 0.57. So we have 6.57. 6.57. Also, we have an anti-clockwise movement which will be positive now because we are considering force on the right. So it will be plus 400. And we have a clockwise movement because of this force, which is of the UDL force. And that is why it is negative. So 28.5 is the force and the distance is 0.285. Yeah. So you can calculate this. FGY we have 28.54 into 6.57 plus 400 minus 28.5 into 0.285. We have 579.38. 579.38. As you can see, it is coming out to be like maximum till now, which we have calculated. It is maximum from till now. It is the maximum most which we have calculated. Most amount of bending moment. So let us see if you are getting value more than this, because we should not get value more than this. The shear force is going 0 at that particular point, at this particular point. So bending moment should be measured at this point. Yeah, we have a bending moment at E, because we have calculated at D, we need bending moment at E. We have FGY into 6 anti-clockwise again plus 400. So FGY is at 28.54 into 6 plus 400. We have 571.24, and bending moment left of F is because there is a certain movement, so we need to consider left and right of that point. We have left of the F as a 28.54, which is the FGY into 3 anti-clockwise, so that is y positive, plus 400, so 485.62. Bending moment right of F is nothing but 28.54 into 3 anti-clockwise, so that is y positive, 85.61. Yeah. We can now draw the bending moment diagram from all the values that we have calculated. A, B, C, D, E. It is somewhere here G. So we have at A we have 0, at B we have 213.88, at C we have 385.33, 528.24 at D, 579.38 at some point X. So this is somewhere, let us say X. So 579.38, 571.24. So 571.24 at E. Left of at F it is 485. So somewhere here let us say 485.62, and right of F it is 85. So 85.62, and G it is 0. So again, wherever there is a UDL, you need to apply the parabolic condition of the shear force. So this is the parabola, let us say. Between D and E, as you can see in the diagram, there is a UDL. So the shear force will vary linearly, and bending moment will vary parabolically. Rest you can just join using straight lines. Yeah. This is how you can draw your bending moment diagram for this particular problem. Thank you.